The purpose of this video is to answer some common questions from Worksheet 2 in our Probability chapter. Take a minute, pause the video, and grade your answers. You'll see I wrote at the top of the page the formulas for permutations and combinations. You need to have these memorized. Notice that the combinations has the extra r factorial in the denominator, and that makes it so that there are less options. So if you're having a hard time remembering the difference between the formulas, just remember that when order matters, there are more choices. So that is why the formula that we have for permutations will end up with more results. The combinations formula is going to be smaller, a smaller answer, because you are also dividing by r factorial. Alright, what I did here was I picked a couple questions that students usually ask me about that I would have gone over had I been in class. So the first one is problem 6. And for this problem, what you're going to want to do is you want to start by writing out the formula for the permutations of n perm 5. So we're going to start by saying that we have n factorial divided by n minus 5 factorial equal to 12 times n factorial over n minus 3 factorial. Now at this point what I would do is I would go ahead and I would cross multiply. And when I cross multiply, what I'm going to do is I'm going to recognize that the n factorials cancel on each side. And then I'm just going to multiply this over to the other side. So what I end up getting is n minus 3 factorial over n minus 5 factorial is equal to 12. From here, recall we talked about rewriting the larger factorial in terms of the smaller factorial. And the larger factorial would be the n minus 3. Now if you're struggling with figuring out which one is larger, just plug in an arbitrary number for n. For example, if n were equal to 10, then 10 minus 3 would be 7, and 10 minus 5 would be 5. And the 10 minus 3 would give us a larger answer. Therefore, the n minus 3 factorial is the larger factorial. Now when you're expanding a factorial, remember you want to take away 1 each time. So I will start with n minus 3, and if I subtract 1, I get n minus 4, subtract 1, n minus 5, woohoo, we got a match! Put an exclamation point on the bottom because we are just oh so excited. And then my n minus 5 factorials are going to cancel off. And now what I'm left with is I can put all these two parentheses together, n squared minus 7n plus 12 is equal to 12. The 12's cancel, factor out the n, and I get n times quantity n minus 7 equal to 0. From here, the two algebraic solutions are n equals 0 and n equals 7. However, it's not possible to have n be smaller than the number that I am choosing. In any permutation scenario, n has to be greater than or equal to r. Otherwise, it doesn't make any sense. So we're going to cross off the 0, and our answer for n is going to be 7. The next problem I'm going to focus on is problem 12. And in this problem we have 7 male members, 6 female members, and 3 drug-sniffing dogs that make up the SWAT team. The first question says, how many ways are there to select a group of 4 people and 2 dogs? So what we want to do is we want to say, okay, I need to choose 4 people, and there are a total of 13 people when you put together the males and females. So I'm first going to do 13 choose 4, and then I'm going to choose 2 dogs, and there are 3 dogs to choose from, so I will have 3 choose 2. And when I find all of the ways that I can choose people and all of the ways that I can choose dogs, I then multiply those choices together, and I get the result of 2,145. In part B, the question says, how many ways are there to select a group of 2 men, 3 women, and 1 dog? So using the same idea, I say, alright, well I have 7 males to choose from, and of those 7 I'm going to pick 2. And then I have 6 females to choose from, and of those 6 I'm going to choose 3. And then I have 3 dogs to choose from, and of those dogs I'm going to choose 1. And I multiply all these together, and I get 1,260. Now this next question is a little bit different, and there is a key word in here that we really want to pick up on. It says, how many ways are there to select 4 people with at least 2 being women? The word at least is very important. When we hear the word at least, or at most, what that means is that we are going to need to add. All right, we have to find multiple solutions and add them together, because there are several ways that we can make this happen. We're going to pick 4 people, and of those 4 people, we could have 2 women, we could have 3 women, we could have 4 women. So we need to consider all of the ways to have this happen. So first, we're going to have 2 women. Then we can also find combinations with 3 women. And lastly, we can find combinations with 4 women. Now, if I am choosing 2 women, that means I'm choosing 2 males. And I had 7 males, so I'm going to say 2 women and 2 men, or 3 women and 1 man, or 4 women and 0 men. So now if we consider these options, out of all of the women that we have, there are a total of 6. So this would be 6 choose 2, together with, out of my 7 males, 7 choose 2. My next scenario is 6 choose 3, together with 7 choose 1. And my last scenario is 6 choose 4, together with 7 choose 0. Now technically 7 choose 0 is just equal to 1, so it's not even really necessary to write. It doesn't change the product. However, it is helpful to write so that we remember to consider it. Now, one thing I want you to notice is that each of these options, basically what's happening is that these numbers are changing. The end numbers are changing to reflect all of the different ways that we could have at least 2 women. And now that we have our setup done, now we're going to go ahead and we're going to plug this in the calculator, and we will end up getting 315 plus 140 plus 15 equaling 470 possible ways to have at least 2 women. The next problem that I want to focus on is number 15. Whenever we're working with card problems, it's important that you have a good understanding of how a deck of cards operates. If you don't, please Google deck of cards. You can get a nice graphics or summary or whatever to help you understand that. Some of the basics: there's 52 cards in a deck. We don't count the jokers. Within those 52 cards, there are 4 suits, and within those 4 suits, there are 2 that are red and 2 that are black. There are 13 cards per suit. Of those 13 cards, there are 3 face cards: Jack, Queen, King, and then an ace. The first question asks us to pick out how many 2-card hands there are. There are no specifics other than the fact that we are just picking out 2 cards. Well, out of my 52 cards, if I want to choose 2, I just do 52 choose 2, and there are 1,326 options. In part B, it says the number of 3-card hands where every card has the same value. If every card has the same value, that means, for example, that your 3-card hand has maybe 2, 2, and a 2, or a Jack, Jack, Jack. So there's 2 things that we have to consider. First, we have to pick the value, and then once we've picked the value, we have to choose 3 of that value. So if we think about this, there are 13 different values in each suit. There's an ace, there's 2 through 9, and then Jack, Queen, King. So first you have to figure out, okay, well, what is it that you have in your hand? Are they all 2s? Are they all 6s? Are they all Jacks? What are you carrying? So of the 13 cards that you could have 3 of a kind, we have to first pick which card we have. Then, once we've done that, once we've decided, all right, I'm picking 3 2s, well, there's actually 4 2s, so we have to do 4 choose 3. A lot of times people forget the first part, and they just do the second part, 4 choose 3. But the problem is that 4 choose 3 only tells you how many ways you can pick 3 out of 4 cards. It does not take into the fact that once you have figured out all of the ways that you can choose 3 of those 4 cards, that you actually could have done that for each of the different values in your deck. And that's why we have to multiply by this first one. And our final answer here will be 52. In part C, the question says the number of 5 card hands with all 5 cards of the same suit. Alright, so similarly to part B, not only do we have to consider how we can pick 5 cards within the same suit, we also have to pick a suit. So first, let's say, alright, let's pick a suit. There are 4 suits that I can pick from, and I'm going to pick one of them. So I want 4 clubs, or I'm sorry, 5 clubs, or I want 5 hearts. I have to figure out which suit am I working with. Then, once I've picked my suit, now I have to choose 5 cards from this suit. And we've already said that each suit has 13 cards, so I will do 13, choose 5. And then I'm going to multiply both of these together. And the end result is 5,148. Now part D is where things get interesting, because again we have that code word, at least. So the number of 2 card hands with at least 1 face card. Now we're lucky here because I'm only talking about 2 card hands. Had I been talking about a 4 card or a 5 card hand, well then I would have had a lot more options. However, it's only the number of 2 card hands with at least 1 face card. So basically I have, how many ways can I get exactly 1 face card? Plus, how many ways can I get exactly 2 face cards? And remember, when we see the word at least, we want to think add. So if we see at least or at most, it means that we need to add different options. Alright, so if I have 1 face card, then that means I have 1 non-face card. And since there are 3 face cards per suit, and there are 4 suits, that means that there are a total of 12 face cards. So out of those 12, I'm going to choose 1, and then I have to choose a non-face card. Again, if there are 52 cards in my deck and 12 have faces, then that means 40 do not. So this would be 1 face and 1 non-face. However, I could also have 2 faces, and if I choose 2 face cards, it's 12 choose 2, and then 40 choose 0. And again, the 40 choose 0 does not have to be there. It's more of a placeholder to remind you that you are not picking any non-face cards. And after we multiply these together, then we will get 480 plus 66, which gives us 546. Okay, this last problem has a couple things that we need to consider. We have 3 different hardcover books and 5 different paperback books that are placed on a shelf. How many ways can they be arranged if the hardcover books have to stay together? So think of this like, let's say you've got your DVD rack and you want to always keep your Star Wars trilogy together. You don't really care if they go in order of the first, second, and third, but you always want them together. So think of this like we have our block of hardcover books. 1, 2, 3. And then we have 5 paperback books. 1, 2, 3, 4, 5. And we really don't care where the hardcovers go. For example, it could go 1, 2 paperbacks, and then 1, 2, 3 my hardback, and then 1, 2, 3 paperbacks. So we don't really care where the hardcover books go as long as they are together. So really and truly what we are moving around is 5 paperbacks and 1 hardcover cluster. So we are really permutating 6 objects. So you want to first think about this like 6 objects permutate 6 ways. However, once we have found where the hardcover books are actually going to stop, then we can rearrange those hardcover books within there. And so we need to do 3p3 for those hardcover books. So the first option, this is moving around the 5 paperbacks and the hardcover group. And then this right here is moving around the 3 hardcovers within where they end up stopping. And when we multiply those together, we end up getting 4,320.